Picture a time before time when the universe was nothing more than a swirling sea of darkness, an endless void waiting to ignite. This was the cosmic dawn, the moment the first stars flickered to life, piercing the endless night with their brilliant glow. These ancient beacons didn't just light up the cosmos, they rewrote its very story, forging the building blocks of everything we know today. Yet, despite their monumental role, these first stars and galaxies remain some of the most elusive mysteries in the universe. How did they form? What secrets do they hold about the infancy of existence itself? And why, after decades of searching, do so many of their puzzles still defy our understanding? We're about to embark on a journey into the deepest reaches of cosmic history where the answers aren't just hidden, they're woven into the fabric of space and time. Think about it, every atom in your body, every speck of dust on Earth, even the very screen you're watching right now, all of it traces back to those first celestial giants. Their explosions seeded the universe with the ingredients for life. Their light stretched across billions of years to reach us, carrying whispers of a world we can barely comprehend. But here's the astonishing part. We've only just begun to decode their messages. From ghostly galaxies that vanish without a trace to stars so massive they defy the laws of physics, the early universe is a treasure chest of enigmas, each one more baffling than the last. That's where you come in. Over the next 30 mysteries, we'll unravel the cosmic riddles that have stumped scientists for generations. We'll peer into the void, hunting for clues left behind by the universe's first architects. We'll confront the limits of our knowledge, question everything we think we know, and maybe, just maybe, catch a glimpse of the truth hidden in the starlight. This isn't just a story about the past, it's a key to understanding our place in the cosmos. So buckle up, the universe's greatest secrets are waiting, and they're more incredible than you've ever imagined. Long before galaxies spiraled into existence, before planets took shape, even before the elements that make up our world were forged, the universe was a silent, starless expanse. Then, out of the darkness, something extraordinary happened. Gravity began to pull together the sparse clouds of hydrogen and helium left over from the Big Bang, compressing them until ignition. The first stars were born, and they were unlike anything we see today. Scientists call them population 3 stars, cosmic titans that may have been hundreds of times more massive than our Sun. Imagine a star so colossal it could eclipse our entire solar system, burning at temperatures so extreme its light was ultraviolet, a searing beacon in the infant cosmos. But here's the catch, we've never seen one. These primordial giants lived fast and died young, their lifetimes measured in mere millions of years, a blink in cosmic terms. When they reached the end of their brief, brilliant lives, they didn't fade quietly. Instead, they exploded in cataclysmic supernova, scattering the first heavy elements carbon, oxygen, iron into the void. These ashes became the building blocks for future stars, planets, and even us. Yet their fleeting existence means they vanished long before telescopes could capture them. All we have are shadows, clues hidden in the faintest light from the edge of time. Astronomers hunt for these ghosts by studying the oldest light in the universe, the cosmic microwave background, and searching for chemical fingerprints in later generations of stars. Some theories suggest population 3 stars might have formed in isolation, while others propose they clustered in the first protogalaxies. But one thing's certain, if we could find just one, it would rewrite our understanding of how the cosmos grew up. These stars weren't just the first lights, they were the universe's first alchemists, transforming simplicity into complexity, darkness into a legacy that still shines in every atom around us. The hunt for these ancient cosmic giants, population 3 stars, is like searching for footprints in the sand after the tide has washed them away. We know they must have existed, yet the universe seems determined to hide them from us. One reason is their staggering speed of life and death. Unlike modern stars that can shine for billions of years, these primordial beasts burn through their fuel in a cosmic heartbeat. Imagine a firework that explodes with unimaginable brilliance, then vanishes before you even finish blinking. That's how quickly these stars lived, died, and scattered their remains across the cosmos. By the time light from the most distant galaxies reaches our telescopes, their era has long since passed, leaving only faint echoes in the chemical makeup of younger stars. Then there's the problem of ingredients. The early universe was a far simpler place, just hydrogen, helium, and trace amounts of lithium. Without heavier elements to help cool collapsing gas clouds, these first stars may have formed under conditions we've never witnessed. Modern stars are born in nurseries dusted with carbon and oxygen, which act like cosmic refrigerants, allowing gas to clump into smaller, more stable bodies. But population 3 stars had no such luxury. They grew unchecked into behemoths, their sheer size making them unstable and prone to self-destruction. It's like comparing a delicate glass sculpture to a mountain of dynamite. One is built to last, the other destined to vanish in a spectacular blast. Our telescopes face another obstacle: distance. The light from these stars has traveled over 13 billion years to reach us, stretched and faded into the infrared by the expansion of the universe. It's like trying to read a letter that's been left out in the rain. The ink has run, the paper is crumbling, and only fragments of the original message remain. Even our most advanced observatories, like the James Webb Space Telescope, are straining to pick up these whispers from the cosmic dawn. Some astronomers are hunting for indirect clues, like the unique chemical signatures these stars would have left behind in ancient gas clouds. Others are simulating their fiery births and deaths in supercomputers, hoping to predict where their remnants might linger. But here's the twist: some theories suggest we might have already spotted their descendants. A handful of ultra-distant galaxies appear suspiciously bright and mature for their age, as if they were built on the ashes of something even older. Could these be the children of population 3 stars, their legacy written in starlight we're only now learning to decode? Or could these elusive giants still be hiding in plain sight, disguised by time and distance? Every unanswered question pulls us deeper into the mystery, reminding us that the universe's first chapter is still being written, one discovery at a time. Hidden in the darkness of the early universe, an invisible architect shaped the birth of the first star's dark matter. This mysterious substance, making up 85% of the universe's mass, didn't just watch from the sidelines. Its gravitational pull may have been the cosmic scaffolding that allowed gas clouds to collapse into those first brilliant stars. Picture a vast, invisible hand gathering hydrogen like sand into dunes, compressing it until nuclear fusion sparked to life. Without dark matter's relentless tug, those primordial gas clouds might have remained too diffused, too scattered to ever ignite. Yet unraveling dark matter's role is like trying to reconstruct a crime scene where the only witnesses are shadows. We know it's there. Its gravitational fingerprints are all over the cosmos, bending light and sculpting galaxies, but we've never directly seen it interact with ordinary matter. In the early universe, dark matter's gravity likely created dense halos, pulling hydrogen and helium into their clutches. These halos acted as cosmic cauldrons where gas pooled, heated, and eventually birthed stars. Some theories even suggest dark matter particles might have collided within these halos, releasing energy that further heated the gas, accelerating star formation. Imagine tossing logs onto a fire, only these logs were made of something we still can't identify. The debate gets thornier when we ask, did dark matter leave behind traces we can detect today? Some astronomers hunt for odd stellar patterns, ancient stars orbiting in unexpected ways, as if still feeling the ghostly tug of long-vanished dark matter structures. Others analyze the faint afterglow of the Big Bang for ripples caused by dark matter's early influence. There's even a tantalizing possibility that the very first stars formed differently in regions where dark matter was denser, leaving behind chemical signatures in the universe's oldest gas clouds. But here's the twist. Dark matter might not have been the only player. Alternative theories propose that magnetic fields or turbulence in the early gas could have rivaled its gravitational pull, creating stars without dark matter's help. It's a cosmic tug-of-war, and we're still deciphering who or what was the true hero of this story. One thing's certain: if we could pinpoint dark matter's role in those first moments of starlight, we'd unlock secrets not just about the past, but about the invisible skeleton holding our universe together today. The search isn't just about stars, it's about understanding the hidden forces that built reality itself. If you could travel back to watch the first galaxies form, you wouldn't recognize them. Forget the elegant spirals of Andromeda or the smooth ovals of modern ellipticals. The universe's earliest galaxies were cosmic misfits, sprawling and misshapen, like lumps of celestial dough still waiting to rise. These primordial giants weren't just different in appearance, they were chaotic by design, their clumpy, irregular forms betraying a universe still figuring out how to build order from chaos. The reason lies in their raw materials. Unlike today's galaxies, which recycled generations of stardust into new stars, the first galaxies emerged from nearly pure hydrogen and helium, with no heavy elements to help gas cool efficiently. Without those ingredients, gravity struggled to sculpt neat structures, leaving behind fragmented, turbulent systems. Imagine trying to build a sandcastle with dry sand. It collapses into uneven piles no matter how carefully you shape it. That's how these galaxies formed, not as precise designs, but as haphazard assemblies of star-forming blobs, each one a frenzied nursery for the universe's earliest stars. The James Webb Space Telescope is finally giving us front-row seats to this cosmic chaos. Peering over 13 billion years into the past, its infrared eyes have spotted galaxies so bizarre they defy classification. Some with multiple bright knots of starlight strung like beads on a string, others with stars scattered like shrapnel from an explosion. One discovery, dubbed the cosmic pretzel, shows two star-forming regions twisted together in a gravitational dance, a snapshot of two protogalaxies caught mid-collision. These aren't just oddities, they're blueprints showing us how small, chaotic structures merged over eons to build the grand galaxies we see today. Supercomputer simulations add another layer to the mystery. When scientists recreate these ancient conditions in virtual universes, the galaxies that emerge look eerily similar to Webb's snapshots: patchy, asymmetrical, and riddled with violent bursts of star formation. But here's the puzzle: some real early galaxies appear too massive, too mature for their age, as if they skipped steps in the cosmic instruction manual. Did dark matter give them a head start? Were there unknown physical processes at play? Every new image from Webb deepens the enigma, revealing a dawn of galaxies far stranger and more varied than we ever predicted. What's clear is this: the first galaxies weren't just younger versions of the ones we know. They were a different breed altogether, forged in a universe where the rules were still being written. And as we piece together their shapes, we're not just uncovering their secrets, we're learning how chaos gave birth to the ordered cosmos we call home. Somewhere in the darkness between the birth of the first stars and the galaxies we know today, the entire universe underwent a radical transformation, one so profound it reset the very nature of space itself. This was the epoch of reionization, a cosmic upheaval where the thick fog of neutral hydrogen that had blanketed the early universe was suddenly torn apart, atom by atom, by the fierce light of newborn stars and galaxies. Picture a frozen lake cracking under the first warmth of spring, only on a scale so vast it reshaped the cosmos. But how exactly did this happen? The leading theory suggests that ultraviolet radiation from those first massive stars, population 3, and the earliest galaxies ripped electrons from hydrogen atoms, ionizing the gas and clearing the way for light to travel freely. It's like opening the curtains in a pitch-black room, allowing sunlight to flood in for the first time. yet the details of this process are anything but clear. Observations from the most distant quasars, bright beacons powered by supermassive black holes, show patches of the universe that were already fully ionized when the cosmos was less than 1 billion years old. Meanwhile, other studies of ancient hydrogen clouds suggest reionization might have been a slower, more uneven process, with some regions remaining shrouded in neutral gas far longer than expected. The James Webb Space Telescope is now uncovering even deeper contradictions. Some of the earliest galaxies it's detected appear too faint and too few to have powered reionization alone, leaving astronomers scrambling to find missing sources of ionizing radiation. Could there have been an earlier generation of stars or galaxies we haven't spotted yet? Or might black holes gorging on gas in the hearts of those first galaxies have contributed more high-energy photons than we thought? There's even a fringe hypothesis that decaying dark matter particles could have played a role, their exotic physics releasing just enough energy to help strip electrons from hydrogen. The timing is equally baffling. Chemical fingerprints preserved in the atmospheres of the Milky Way's oldest stars hint that reionization might have begun locally, near regions where stars formed densely before spreading like cosmic wildfire. But simulations suggest it should have been a more uniform process, with radiation flooding outward in predictable waves. This mismatch between theory and observation has forced scientists to reconsider everything from the efficiency of early stars at producing ionizing photons to how easily those photons escape their host galaxies. What's at stake isn't just a chapter of cosmic history, it's the origin of the transparent universe we inhabit today. Without reionization, light from stars and galaxies would still be absorbed by that primordial hydrogen fog, leaving our telescopes blind to nearly everything beyond our own galaxy. Solving this puzzle means understanding not just how the first structures lit up the cosmos, but how they forged the conditions that allowed the universe to become visible, measurable, and ultimately knowable. Every new observation peels back another layer, revealing an era far more complex and far more mysterious than we ever imagined. At the heart of nearly every modern galaxy lurks a supermassive black hole, a cosmic predator millions or even billions of times heavier than our Sun. But here's the puzzle that keeps astronomers awake at night. Some of these monsters existed when the universe was less than 700 million years old. That's like finding a skyscraper in the middle of a Stone Age village. How could black holes grow so unimaginably massive in the cosmic blink of an eye? One radical possibility is that the first supermassive black holes didn't form from dead stars at all. Instead, they might have been born straight from collapsing clouds of primordial gas skipping the star phase entirely. Picture a vast pool of hydrogen, so dense and hot that gravity overwhelms all other forces, causing it to implode directly into a black hole. These direct collapse black holes could have started life weighing thousands of solar masses, giving them a head start on their journey to becoming galaxy-devouring giants. Simulations show these exotic objects would form in rare, ultra-dense regions where gas couldn't fragment into stars' cosmic dead zones where only a black hole could take root. But there's another contender in this mystery: runaway star mergers. In the crowded cores of early galaxies, massive stars might have collided and merged repeatedly, building up stellar behemoths hundreds of times heavier than our Sun. When these Frankenstein stars finally exploded, their remnants could have collapsed into unusually large seed black holes. Over time, voracious feeding on surrounding gas and even swallowing smaller black holes could have turbocharged their growth. Imagine throwing logs onto a bonfire, only instead of wood, its entire stars vanishing into the abyss. The James Webb Space Telescope is now spotting baffling clues. Some ancient galaxies host black holes seemingly too large for their galactic homes, outweighing their host galaxies by factors that defy modern astrophysics. Others show strange, super-bright quasars, black holes shining with the light of trillions of suns existing far earlier than models predict. Could these be the smoking guns of direct collapse? Or evidence of black holes merging at rates we've never witnessed? The stakes couldn't be higher. If supermassive black holes grew through sheer appetite alone, they'd need to consume gas non-stop at impossible rates, violating known physics. But if they started as super-sized seeds, it reshapes our entire understanding of cosmic evolution. What's clear is that these early giants weren't just outliers, they were the rule, sculpting their host galaxies through violent outbursts of energy that determined how stars formed and where. Unlocking their origins isn't just about black holes, it's about deciphering how the universe learned to build itself. Each new discovery peels back another layer, revealing a dawn of chaos where the rules we know didn't just bend, they were rewritten. Galaxies come in all sizes, from sprawling spirals to tiny dwarfs, but when we look back at the early universe, something strange happens. Entire categories seem to be missing, like a family photo with no teenagers, only grandparents and infants. Specifically, there's a puzzling shortage of mid-sized galaxies from cosmic dawn. Theories predicted these intermediate mass galaxies should be everywhere, bridging the gap between small clumps of stars and the colossal giants we see today. Instead, observations reveal a cosmic desert where mid-sized galaxies ought to thrive, and astronomers are scrambling to figure out why. One leading explanation is that these galaxies didn't disappear, they simply never had a chance to grow. In the chaotic early universe, mergers were constant, with smaller galaxies smashing together like bumper cars. A mid-sized galaxy might form, only to be swallowed whole by a larger neighbor before telescopes could spot it. Simulations show these collisions happening at breakneck speeds, leaving behind few survivors in the intermediate mass range. Imagine a forest where saplings are either snapped up by towering trees or trampled before they can mature. That might be the fate that befell these missing galaxies. But mergers aren't the only suspect. Another possibility is that star formation in these galaxies was stifled early on. Ultraviolet radiation from the first stars could have heated surrounding gas, making it too energetic to collapse into new stars, strangling these galaxies in their infancy. Or perhaps supernova blasted away their fuel, leaving them stuck in a developmental limbo. Observations from the Hubble and Webb telescopes reveal some early galaxies with shockingly low star formation rates, as if something pressed pause on their growth. The plot thickens when we consider dark matter's role. These mid-sized galaxies would have formed in halos of dark matter with very specific mass ranges, halos that might have been particularly vulnerable to external forces. If nearby massive galaxies or cosmic radiation disrupted these halos, they could have prevented the gas inside from cooling efficiently, stunting galaxy growth. It's like trying to bake a cake in an oven that keeps turning off. The ingredients are there, but the conditions never quite align. Yet the most tantalizing clue comes from chemical fingerprints. Some ancient dwarf galaxies, potential building blocks of mid-sized systems, show unusual abundances of heavy elements, suggesting their star formation was abruptly cut short. Did they exhaust their fuel? Were they stripped bare by larger galaxies? Each answer raises new questions, painting a picture of an early universe far more violent and unpredictable than we ever imagined. The absence of these galaxies isn't just a cosmic curiosity, it's a missing link in our understanding of how structure evolved. If mid-sized galaxies were vanishing acts, it changes how we model everything from star formation to dark matter's influence. Every blank space in our cosmic maps is a reminder. The universe's history isn't just written in the stars we see, but in the ghosts we're still learning to trace. Scattered across the early universe like cosmic lighthouses, Lyman-Alpha Blobs are among the most bizarre structures ever observed. Enormous clouds of hydrogen gas, some stretching hundreds of thousands of light years, glowing with an eerie ultraviolet hue. Named after the specific wavelength of light they emit, These mysterious behemoths shouldn't exist under standard models of cosmic evolution. Yet there they are, defying expectations, their origins shrouded in a debate that cuts to the heart of how the universe organized itself after the Big Bang. One faction of astronomers believes these blobs are stellar nurseries on a scale we've never witnessed, regions where gas collapsed so violently it birthed entire generations of stars at once. Picture a whirlpool of hydrogen, swirling and compressing until pockets ignite like firecrackers in a chain reaction, flooding the surrounding gas with enough energy to make it glow across interstellar distances. Supporting this idea, some blobs contain clusters of young, ferociously bright stars, their ultraviolet radiation ionizing the hydrogen around them like a match held to paper. These star-making factories could explain why certain blobs appear lumpy or filamentary, as if sculpted by the stellar winds of countless newborn suns. But there's a competing theory. What if these blobs aren't powered by stars at all? Some glow too uniformly, too smoothly, as if lit from within by an invisible engine. That's where quasars enter the picture, supermassive black holes voraciously devouring gas and spewing out torrents of radiation. Hidden deep within these hydrogen clouds, a quasar could act like a flashlight in a fog bank, its intense beams scattering off the surrounding gas to create the illusion of a diffuse glow. Recent observations have revealed that some blobs do indeed harbor quasars at their hearts, their presence betrayed by the faintest flickers of X-rays bleeding through the gas. Yet others show no trace of central monsters, leaving the question wide open. The confusion deepens when we examine the blobs' environments. They often sit at the intersections of cosmic filaments, thick tendrils of dark matter where galaxies congregate like pearls on a string. This placement suggests they might be feeding hubs, drawing in gas from the surrounding web and funneling it toward growing galaxies. Simulations show that gas crashing into these dense nodes could shock heat to millions of degrees, triggering the Lyman-Alpha emission we observe. If true, these blobs aren't just bystanders, they're active players in galaxy formation. Their glow a side effect of the universe's largest-scale plumbing. Then there's the wild card, cooling radiation. Some theorists argue that the blob's light might come from hydrogen atoms releasing energy as they settle into lower energy states, like a hot pan gradually radiating away its heat. In this scenario, the gas doesn't need stars or quasars to glow. It's simply cooling after being heated by gravitational collapse or collisions with other gas clouds. The challenge: this process is notoriously hard to distinguish from star or quasar-driven emission, leaving astronomers to tease apart subtle differences in the blob's spectra for clues. What makes these enigmas so tantalizing is their sheer scale. A single blob can outshine entire galaxies, its light traveling billions of years to reach us, carrying snapshots of conditions we can't replicate in any lab. Whether they're signposts of hidden quasars, cosmic construction zones, or something entirely unforeseen, one thing is certain: solving their mystery could rewrite how we understand the universe's most formative era. Each observation peels back another layer, revealing a dawn of existence far stranger and far more luminous than we ever dreamed. The first stars weren't just different in size or brightness, they burned with a purity modern stars can't replicate. Picture a flame fueled by nothing but the simplest elements, hydrogen and helium, untouched by the contamination of heavier atoms. This pristine chemistry didn't just change how these stars shone, it rewrote the rules of nuclear fusion itself. In today's universe, stars like our Sun benefit from trace amounts of carbon, nitrogen, and oxygen elements that act like cosmic catalysts, smoothing the path for hydrogen atoms to fuse into helium through the C&O cycle. But the first stars had no such shortcuts. Their fusion relied solely on the proton-proton chain, a slower, more laborious process where hydrogen nuclei smashed together directly, releasing energy bit by bit. The difference is like trying to start a fire with damp wood versus a blast of pure oxygen. One sputters, the other roars. Without heavier elements to help, these ancient stars had to burn hotter and denser to sustain themselves, which may explain why they grew so unimaginably massive. But here's the twist: their simplicity also made their deaths far more dramatic. When modern stars exhaust their fuel, the presence of heavier elements allows their cores to cool and collapse in stages, often leaving behind white dwarfs or neutron stars. Population 3 stars, though, faced a stark choice: burn out or explode with no middle ground. Their pure helium cores, free of impurities, could reach staggering temperatures before collapsing. Some models suggest these stars might have detonated as pair instability supernova, explosions so violent they left no remnant behind, just a burst of raw energy and a spray of newly forged elements scattering into the void. These explosions were the universe's first alchemy labs. For the first time, hydrogen and helium fused into carbon, oxygen, and heavier elements, seeding the cosmos with the ingredients for future stars, planets, and life. Yet even this process was different from what happens today. Modern supernovae are enriched by generations of prior stars, their debris laced with a complex cocktail of metals. The first supernova, though, produced a far simpler set of elements, almost like a chef working with only salt and pepper, while later generations had access to an entire spice rack. Astronomers search for these chemical ghosts in the oldest stars still shining. Some metal-poor stars in the Milky Way's halo bear the fingerprints of just 1 or 2 population 3 supernova. Their atmospheres oddly rich in certain elements like strontium or europium, but devoid of others. It's as if we're reading a recipe written in the universe's infancy, one that calls for ingredients we've since forgotten how to make. The legacy of this primordial chemistry isn't just a cosmic curiosity. It's a reminder that the universe's first steps toward complexity were hesitant, uneven, and far more fragile than we ever imagined. Every atom forged in those early infernos carries a story, one we're only beginning to decode. When the universe's first stars reached the end of their brief, fiery lives, they didn't just fade away. They exploded with a violence that shaped everything that followed. But how these cosmic titans met their demise is one of the most heated debates in astrophysics. Did they detonate in supernova so colossal they outshone entire galaxies, scattering the first heavy elements across the cosmos? Or did they collapse silently into black holes, vanishing without a trace and leaving the universe to wait for later generations of stars to seed it with the building blocks of planets and life? The answer may lie in the chemical fingerprints they left behind. Population 3 stars were so massive, some weighing over 300 times the mass of our Sun, that their deaths defied the rules governing modern stars. For stars this size, conventional supernova might not even be possible. Instead, they could have undergone a phenomenon called pair instability supernova, where the core becomes so hot that photons spontaneously convert into electron-positron pairs. This steals energy from the star's core, causing it to collapse uncontrollably, until runaway fusion triggers a detonation so powerful it obliterates the star completely, leaving no remnant behind. The energy released would be almost incomprehensible, up to 100 times brighter than a typical supernova, with shockwaves capable of sterilizing entire galaxies of fledgling planets. But not all primordial stars may have died this way. Simulations suggest some could have collapsed directly into black holes if they were slightly less massive or rotated rapidly enough to stabilize their cores. In these cases, the star's outer layers would have plummeted into the abyss without the fireworks of a supernova, locking away the star's heavy elements forever. This creates a bizarre paradox. The very stars that forged the universe's first carbon, oxygen, and iron might have stolen those ingredients back, trapping them inside event horizons before they could enrich surrounding gas clouds. Astronomers hunt for clues in the oldest stars still shining today. Metal-poor stars like He 1307-0402, found lurking in the Milky Way's halo, contain bizarrely lopsided chemical compositions abundant in some heavy elements like strontium but nearly devoid of others. This imbalance suggests they formed from the ashes of just one or two population 3 supernova, rather than a well-mixed soup of many stellar explosions. Other ancient stars show no traces of these elements at all, hinting they might have been born near stars that imploded quietly, contributing nothing to the chemical legacy of the cosmos. The James Webb Space Telescope is now peering even further back, searching for the ghostly afterglow of these explosions in distant gas clouds. One theory predicts that pair instability supernova should leave behind a distinct chemical signature, an overabundance of elements with even atomic numbers like oxygen and silicon, since their fusion processes favor pairing protons. If Webb spots clouds with this fingerprint, it could confirm that at least some first stars died in these spectacular blasts. Meanwhile, gravitational wave observatories listen for the echoes of ancient black hole mergers, which might reveal how many primordial stars chose the path of silent collapse. What's at stake isn't just a detail of stellar evolution, it's the origin of everything. If most population 3 stars vanished into black holes, the universe's chemical enrichment would have been delayed, potentially altering the timeline for planet formation and life. But if they died in fireworks, they may have jump-started the cosmos with a generosity we're only beginning to measure. Each new discovery peels back another layer of this mystery, revealing a dawn where stars didn't just live and die. They decided the fate of everything that came after. Before the first stars ignited, the universe endured a profound silence, a stretch of time so dark and featureless it's known simply as the cosmic dark ages. Picture a fog so thick not a single beam of light could pierce it, a realm where hydrogen gas hung in a neutral, unlit haze, absorbing any radiation that dared to pass through. This wasn't just an absence of stars, it was a universe in waiting, a canvas blank save for the faint afterglow of the Big Bang slowly fading into oblivion. But darkness doesn't mean emptiness. During this era, the cosmos was subtly shifting. Gravity tugged gently at clumps of dark matter, pulling them together into invisible scaffolds. Hydrogen atoms, still warm from the universe's fiery birth, emitted faint radio waves at a specific frequency, 21 centimeters, a whisper from the void that modern astronomers now chase like a cosmic detective tuning into static for clues. These signals, redshifted by billions of years of cosmic expansion, hold the key to mapping this elusive epoch. The magic of the 21-centimeter line lies in its simplicity. When the spin of a hydrogen atom's electron flips relative to its proton, it releases a photon with that exact wavelength. In the Dark Ages, these emissions were everywhere, painting the universe in radio waves before stars or galaxies existed to drown them out. By studying how these signals vary across the sky, scientists can reconstruct the distribution of gas before the first structures formed, like developing a photograph from a negative no one knew existed. Yet capturing these whispers is staggeringly difficult. The expansion of the universe has stretched their wavelengths to meters or even tens of meters, placing them in a part of the radio spectrum flooded with human-made interference. Cell phones, satellites, and even distant thunderstorms create noise that can drown out the signal. Projects like the Square Kilometre Array and the Lunar Surface Electromagnetics Experiment aim to bypass these hurdles, with telescopes stationed in remote deserts or even on the far side of the moon where Earth's chatter can't reach. What makes this hunt so revolutionary isn't just filling in a blank chapter of cosmic history, it's testing fundamental physics. The patterns in these radio signals could reveal how dark matter shaped the early gas, or even uncover exotic particles that interacted with hydrogen in ways the standard model doesn't predict. Some theories suggest the Dark Ages might have ended unevenly, with patches of the universe ionizing earlier than others, creating a cosmic patchwork invisible to optical telescopes but etched into these radio waves. The stakes couldn't be higher. If we can decode this static, we'll witness the universe's quiet adolescence, the moment before it burst into light. It's a reminder that even in the deepest darkness, the cosmos was never truly still. It was gathering itself for the dawn to come. The James Webb Space Telescope was supposed to solve mysteries, not create them. Yet its first deep-field images delivered a shock. Galaxies blazing with starlight in a universe barely 500 million years old. These cosmic fireballs shouldn't exist. According to our best models, galaxies from this era should be small, dim, and only just beginning to assemble. Instead, Webb found giants mature, massive, and shining with the brilliance of galaxies 10 times their age. It's like finding a skyscraper in the middle of a prehistoric swamp. The root of the crisis lies in galaxy formation timelines, simulations based on the standard cosmological model. Dark matter slowly gathering gas into ever larger structures predict that the earliest galaxies would take billions of years to reach such sizes. Yet Webb's infrared eyes have spotted galaxies like GNZ11, a behemoth already packing hundreds of billions of stars when the universe was less than 3% of its current age. Some even appear shockingly organized, with disk-like structures and central bulges that by all rights should require eons to form. One radical explanation. Dark matter might clump differently than we thought. Current models assume dark matter is cold, slow-moving, and prone to forming halos gradually. But if some dark matter were instead warm, with particles moving at relativistic speeds, it could collapse into dense structures far faster, giving galaxies a head start. There's a catch: warm dark matter would also suppress the formation of the smallest galaxies, a prediction that doesn't quite match observations of nearby dwarf galaxies. Then there's the star formation puzzle. These early giants aren't just large, they're forming stars at rates that defy physics as we know it. In the modern universe, galaxies rarely convert more than a few % of their gas into stars each year. Yet some of Webb's discoveries show star formation rates 100 times higher, as if these galaxies had access to some forgotten cosmic switch that supercharged their engines. One possibility is that the pristine hydrogen of the early universe, free of heavier elements, cooled and collapsed more efficiently, creating ideal conditions for explosive stellar birth. But perhaps the most tantalizing clue lies in black holes. Some of these bright galaxies might owe their luminosity not to stars, but to voracious supermassive black holes at their cores, devouring gas and shining with the light of a trillion suns. If true, it would mean black holes grew to staggering sizes even faster than we imagined, reshaping their host galaxies through violent outbursts of energy. The stakes couldn't be higher. If our models of galaxy formation are wrong, it could ripple through our understanding of dark matter, star formation, even the timeline of cosmic evolution itself. Webb's discoveries aren't just anomalies, they're signposts pointing to a dawn of the universe far stranger and far more luminous than we ever dreamed. Each new observation chips away at our assumptions, revealing a cosmos that refuses to play by the rules we've written for it. Deep within the swirling clouds of gas that birthed the first stars, another invisible force was at work, one that would shape the cosmos in ways we're only beginning to understand. Magnetic fields thread through the universe today, guiding cosmic rays, sculpting galaxies, even influencing how stars form. But their origins trace back to an era so ancient, so chaotic, that the very idea of magnetism seems impossible. How could such orderly forces arise from the primordial soup of the early universe? One leading theory points to the turbulence of star formation itself. As the first gas clouds collapsed under gravity, they didn't fall smoothly. They spiraled, clashed, and sheared, creating swirling eddies of charged particles. These motions could have amplified even the faintest magnetic seeds, like a dynamo cranking up the volume on a whisper. Imagine stirring a cup of coffee with a spoon. The tiny whirlpools you create are a scaled-down version of what might have happened on a cosmic scale. Over time, these flickering fields could have grown stronger, woven into the fabric of galaxies by the violent births and deaths of the first stars. But here's the catch: this process requires a starting point, some initial flicker of magnetism to amplify. That's where things get speculative. Some scientists propose that quantum fluctuations in the early universe, mere instants after the Big Bang, could have imprinted weak magnetic fields on the primordial plasma. Others suggest these fields might have emerged during cosmic phase transitions, moments when the universe cooled enough for fundamental forces to separate, unleashing energy like cracks forming in ice. If true, magnetism isn't just a side effect of cosmic evolution, it's a relic from the universe's most explosive infancy. The debate heats up when we look at extreme environments. Certain ancient stars locked away in the Milky Way's halo exhibit bizarrely strong magnetic fields, as if they formed in regions already steeped in magnetism. Meanwhile, observations of distant galaxies reveal magnetic fields stretching across thousands of light-years, far too vast to have grown solely from local star-forming chaos. Could these be the fingerprints of primordial fields woven into the cosmos before the first stars even flickered to life? Simulations offer tantalizing hints. When researchers model the early universe with and without these primordial seeds, the differences are stark. Fields born from star formation alone tend to be patchy and disorganized, while primordial fields create large-scale structures eerily similar to those we observe today. Yet proving which scenario is correct requires peering back to an era when the universe was a dark, magnetized sea, a challenge even for our most advanced telescopes. The answer might lie in the cosmic microwave background, the afterglow of the Big Bang. Subtle twists in its polarization could, in theory, reveal the presence of primordial magnetic fields. So far, the evidence is elusive, but next-generation telescopes like the Simons Observatory are hunting for these tiny signatures with unprecedented precision. What's at stake isn't just a footnote in cosmic history. Magnetic fields shape how galaxies form stars, how energy travels across the universe, even how planets like Earth shield themselves from deadly radiation. If these fields were there from the beginning, they're not just part of the story, they're among its earliest authors, quietly guiding the universe toward complexity long before the first light dawned. The universe has a dwarf problem not in mythology but in astronomy. According to our best simulations of cosmic evolution, the early universe should be teeming with countless tiny galaxies, each a flickering candle in the vast dark. Yet when we peer into the depths of space, these cosmic runts are nowhere to be found. It's like throwing a party and realizing half your guests never showed up. Except in this case, the missing attendees could rewrite our understanding of dark matter itself. This discrepancy is known as the missing satellites problem, and it's been gnawing at astrophysicists for decades. Supercomputer models based on the cold dark matter framework, the reigning theory of cosmic structure, predict that hundreds of small satellite galaxies should orbit large ones like the Milky Way. Instead, we've only spotted a few dozen. The mismatch isn't just a minor accounting error. It suggests something fundamental might be wrong with how we think the universe assembles itself. One possible explanation lurks in the behavior of dark matter. If this mysterious substance isn't as cold or slow-moving as we assume, but instead slightly warm or faster, its particles could smooth out the smallest clumps, preventing dwarf galaxies from forming in the first place. Picture trying to build sandcastles with dry, fine grains. They slip through your fingers before any structure can hold. Warm dark matter would act like those unruly grains, smoothing away the tiniest cosmic structures while leaving larger ones intact. But dark matter's temperature isn't the only suspect. Another theory points to the brutal environment of the early universe, where ultraviolet radiation from the first stars could have sterilized small galaxies before they ever had a chance to shine. This so-called reionization feedback might have evaporated gas from fledgling dwarfs, starving them of the fuel needed to birth stars. Imagine seedlings trying to grow in a desert. Some might sprout, but most wither before they can take root. Then there's the wild card, supernova. In small galaxies, even a single exploding star can unleash enough energy to blow away remaining gas, halting star formation for good. Some dwarfs we do observe, like Segway 1 in the Milky Way's halo, appear to be relics of this process, ghostly husks where star-making ceased billions of years ago. Could most primordial dwarfs have met this fate, erased by their own violent births? The plot thickens when we examine the dwarfs that did survive. Many orbit our galaxy in a flat plane, like flies trapped on a windowpane, rather than the swarm-like distribution simulations predict. Some even contain puzzlingly few stars relative to their dark matter content, as if something stunted their growth mid-development. The implications are staggering. If dark matter behaves differently than we've modeled, it could reshape everything from galaxy formation to the very nature of this elusive substance. Or perhaps the answer lies in the forgotten physics of the early universe, processes so violent they left only the hardiest galaxies standing. Every new dwarf discovered, every faint star cluster mapped, brings us closer to solving this cosmic case of the missing galaxies. One thing's certain, the universe's smallest structures might hold its biggest secrets. The violent death of a single population 3 star didn't just vanish into the cosmic void, it became the blueprint for everything that followed. When these primordial giants exploded, they didn't merely fade away. They transformed the universe's chemical landscape forever, scattering newly forged elements like cosmic graffiti across pristine gas clouds. This was the universe's first act of recycling, where the ashes of one generation became the building blocks of the next. Modern stars carry traces of this ancient legacy in their DNA. Astronomers practicing stellar archaeology, reading the chemical fingerprints preserved in ancient Milky Way stars, have uncovered shocking clues. Stars like SMSS 0313-6708, found hovering in our galaxy's halo, contain barely 1/10,000th the iron of our Sun. Yet within their atmospheres lurk telltale signatures of just 1 or 2 population 3 supernova, their elemental patterns frozen in time like fossils in cosmic amber. What makes these chemical imprints so revealing is their bizarre imbalance. Unlike modern supernova that produce a broad cocktail of elements, the explosions of population 3 stars seem to have created specific heavy metals in isolation. Some ancient stars show extreme abundances of strontium with almost no barium, or bursts of carbon without accompanying nitrogen, a chemical fingerprint that matches no known stellar process except the pair instability supernova theorized for these first stars. It's as if we're finding shards of broken pottery where each fragment shows only one color from what must have been a broader palette. The delivery system for these elements was just as extraordinary. Shockwaves from supernova ripped through nearby gas clouds at millions of miles per hour, injecting them with heavy elements while simultaneously triggering new star formation. Simulations show these waves could travel hundreds of light years, enriching vast swaths of primordial gas in a single stroke. Imagine tossing a stone into a still pond. Not only does it create ripples, but those ripples carry flecks of paint that permanently tint the water. Yet not all early stars benefited equally. Regions near multiple supernova became chemically diverse quickly, while isolated pockets of the universe remained pristine for much longer. This explains why some ancient stars, like the famously metal poor He-1327-2326, appear nearly untouched by later generations. They formed in cosmic backwaters, far from the polluting influence of their massive neighbors. The most profound implication lies in what these patterns reveal about our own origins. Every carbon atom in your body, every iron molecule in your blood, every calcium speck in your bones was forged in the heart of a dying star. But the very first links in that chain, the population 3 supernova, operated under rules we're only now deciphering. Their unique chemistry set the stage for everything that followed, from rocky planets to organic molecules. By studying these ancient stellar relics, we're not just exploring the past, we're uncovering the recipe for existence itself. Quasars shouldn't exist, at least not as early as they did. These cosmic lighthouses, blazing with the brightness of 1 trillion suns, were already lighting up the universe when it was less than 700 million years old. That's like finding a fully formed city in the middle of a Stone Age wilderness. The mystery isn't just their brilliance, it's how their power sources, supermassive black holes weighing billions of times our sun's mass, grew so monstrously large in what amounts to a cosmic heartbeat. At the heart of every quasar lies a black hole guzzling gas at rates that defy physics as we know it. To shine as they do, these black holes must have devoured staggering amounts of matter, converting it into radiation with terrifying efficiency. But here's the catch: black holes aren't bottomless pits, they're messy eaters. As gas spirals into them through accretion disks, it heats up to millions of degrees, emitting intense radiation that actually pushes back on incoming material. It's like trying to fill a bathtub with the faucet on full blast while the drain keeps splashing water out. At a certain point, called the Eddington limit, the radiation pressure balances gravity, capping how fast a black hole can grow. Yet the earliest quasars smashed through this limit, reaching masses that should have taken billions of years to accumulate. So how did they cheat? One radical idea is that these black holes didn't grow slowly, they were born big. Direct collapse scenarios suggest that in the dense, pristine gas of the early universe, entire clouds could have collapsed directly into black holes weighing tens of thousands of solar masses, skipping the star stage entirely. These cosmic shortcuts would have given quasars a head start, letting them bulk up faster than conventional models allow. Simulations show these behemoths forming in rare, ultra-dense regions where gas couldn't fragment into stars, like cosmic dead zones where only a black hole could take root. But even with a massive seed, feeding a quasar requires a non-stop buffet of gas. That's where another puzzle emerges: the physics of accretion disks. In modern galaxies, magnetic fields and turbulence slow the flow of matter into black holes, but the early universe might have been different. Without heavy elements to cool the gas, disks around primordial black holes could have been thicker, hotter, and more chaotic, allowing matter to plunge inward at breakneck speeds. Some theories even suggest these early disks were super Eddington, with gas pouring in so fast that radiation couldn't escape, trapping energy like a pressure cooker until it erupted in violent outbursts. Then there's the wild card: mergers. In the crowded cores of early galaxies, multiple black holes might have spiraled together, combining their masses in collisions that released gravitational waves and spewed gas into their path. Each merger would have funneled fresh fuel toward the survivors, creating a vicious cycle of growth and feeding. Observations from gravitational wave detectors hint that black hole mergers were common in the early universe, perhaps the cosmic equivalent of throwing logs on a fire. Yet the most tantalizing clues come from the quasars themselves. Spectra of ancient quasars like J034 plus 0002 reveal accretion disks spinning at near-light speeds, their extreme rotation suggesting they'd been feeding relentlessly for eons. Others show chemical fingerprints of rapid star formation in their host galaxies, as if the entire system was caught in a frenzied dance of growth and destruction. The implications are staggering. If black holes could grow this fast, our understanding of cosmic evolution might need a rewrite. Perhaps dark matter played a role, its gravitational pull creating dense gas reservoirs. Or maybe the early universe hid exotic physics processes we've since forgotten, lost to time. Whatever the answer, quasars aren't just relics. They're proof that the universe's infancy was a time of unimaginable violence and creativity, where the rules we know were written in fire. The idea of black holes forming without a star's death sounds like pure science fiction, yet it might be the key to unlocking the universe's earliest secrets. These hypothetical direct collapse black holes wouldn't wait for a supernova. Instead, they'd emerge like cosmic phoenixes, born straight from the collapse of primordial gas clouds in the universe's first 100 million years. Picture a vast pool of hydrogen and helium, so dense and hot that gravity bypasses star formation entirely, crushing the gas into a singularity in one catastrophic plunge. No explosion, no fireworks, just a dark behemoth materializing from the void. What makes this theory so compelling is its ability to solve the quasar riddle. If supermassive black holes had to grow from stellar remnants, even gobbling gas at their maximum rate, they'd never reach billion solar masses so quickly. But a direct collapse black hole could start life weighing tens of thousands of suns, a colossal seed that needs far less time to balloon into the monsters powering early quasars. It's the difference between building a skyscraper brick by brick versus starting with the first 10 floors already intact. The hunt for evidence leads astronomers to extreme environments. Some ancient quasars, like J1342+0928, shine with a brightness that suggests central black holes weighing over 1 billion suns too hefty to have grown from mere stellar corpses. Their host galaxies often show peculiar chemical compositions, lacking the expected enrichment from generations of supernova, as if the black hole arrived before stars could pollute the neighborhood. Other clues come from oddballs like CR7, a distant galaxy glowing with helium-rich starlight but almost no heavier elements, a potential smoking gun for a region where gas collapsed directly into a black hole instead of forming stars. Yet skepticism lingers. Critics argue that without the stabilizing influence of heavier elements, primordial gas clouds should fragment into stars long before reaching black hole densities. Simulations reveal a delicate balancing act. The gas must remain hot enough to resist fragmentation but cool enough to collapse, requiring just the right conditions. Some models suggest that ultraviolet radiation from nearby galaxies could sterilize gas clouds, preventing star formation long enough for direct collapse to occur. Others propose that turbulent magnetic fields or exotic dark matter interactions might tip the scales. The debate now hinges on next-generation telescopes. The James Webb Space Telescope's infrared gaze could spot the telltale glow of helium-rich gas swirling into these young black holes, while gravitational wave observatories might catch the ripples from their mergers. If confirmed, direct collapse wouldn't just explain quasars, it would rewrite the cosmic rulebook, proving that black holes weren't just endpoints for stars but pioneers in their own right. The universe's first darkness might not have been born from light at all. The universe's first stars might not have been lonely giants. Some could have formed in pairs, locked in a gravitational dance that shaped their fiery lives and explosive deaths. Binary star systems dominate the modern cosmos, with over half of Sun-like stars having companions. But did this cosmic duet begin in the earliest days of the universe? The answer could rewrite our understanding of everything from black hole formation to the gravitational waves rippling through space-time today. Picture two population 3 stars, each hundreds of times more massive than our Sun, orbiting so closely their stellar winds collide in showers of ultraviolet radiation. These primordial binaries would have been unlike anything in today's universe, their sheer mass-warping space-time, their nuclear furnaces burning at temperatures that fused hydrogen into helium at staggering rates. When they inevitably died, their fates would have been intertwined. If both collapsed into black holes, they might have spiraled together in a merger so violent it sent ripples across the cosmos, gravitational waves that could still be detectable billions of years later. The evidence for these ancient pairs lies in the whispers of the universe's oldest light. Some ultra-distant quasars appear to be powered by binary black holes, their accretion disks flickering like mismatched headlights as they circle one another. Simulations suggest the first stars often formed in dense clusters where close encounters could have paired them up, while turbulent gas dynamics in the early universe might have spun protostellar disks into fragments that became bound companions. The chemical fingerprints of certain ancient stars also hint at pollution from not one but two supernovae, as if they formed from gas enriched by a binary explosion. But the implications go far beyond stellar archaeology. If binary population 3 stars were common, their black hole remnants could be the primordial seeds of today's supermassive monsters. Mergers between these early black holes would have created a cascade of gravitational waves, potentially detectable by observatories like LIGO or the future Einstein telescope. Some theorists even suggest that the mysterious high-frequency background hum of gravitational waves could be the echo of countless first-generation binary black holes colliding in the dawn of time. Yet mysteries remain. Would the extreme conditions of the early universe, its uniform gas composition, lack of heavy elements, and intense radiation, have favored or suppressed binary formation? Could black holes born from paired stars have merged fast enough to explain the quasars we see, or would their orbits have decayed too slowly? Each question peels back another layer of this cosmic onion, revealing how the universe's first duets might still be shaping the symphony of the cosmos today. The search isn't just about stars, it's about decoding the gravitational echoes of a time when the universe was learning to dance. Some of the universe's earliest galaxies spin with a grace that defies logic, their disks whirling at speeds that leave astronomers scratching their heads. Take galaxy DF244301, a cosmic relic observed when the universe was barely 1 billion years old. Its stars orbit the galactic center so fast that, by conventional physics, the galaxy should have torn itself apart long ago. Yet there it is, spinning undisturbed like a celestial ballet dancer balanced against the odds. This isn't just a fluke. Dozens of these ancient speedsters have been spotted, each one a puzzle wrapped in starlight. The root of the mystery lies in the delicate dance between gravity and motion. In modern galaxies like the Milky Way, rotation speeds are stabilized by vast halos of dark matter, their invisible gravity gripping stars and gas like an unseen hand on a spinning top. But the early universe was a different beast, denser, hotter, and crammed with turbulent gas. For galaxies to rotate this coherently so soon after the Big Bang, their dark matter must have been distributed with uncanny precision, forming perfectly balanced scaffolds around fledgling disks. Some simulations suggest these halos were unusually smooth, lacking the clumpy substructure seen today, allowing gas to settle into orderly rotations almost immediately. But dark matter might not be the only explanation. Another possibility lurks in the chaos of galactic adolescence. Young galaxies grew through violent mergers, colliding and cannibalizing their neighbors in a cosmic free-for-all. Normally, these crashes would leave galaxies misshapen and disordered, but under the right conditions, the chaos could have backfired, spinning disks up like a pinwheel struck by a well-aimed breeze. Imagine two gas-rich protogalaxies grazing each other at just the right angle, their interaction funneling material into a tight, fast-rotating disk instead of a messy splatter. Observations from the Atacama Large Millimeter Array have caught glimpses of this process in action, with some ancient galaxies showing skewed gas flows hinting at past encounters. Then there's the wild card, magnetic fields. Threaded through the early universe's gas, these invisible lines of force could have acted like cosmic guide wires, channeling turbulent motions into coherent rotation. Laboratory experiments with plasma, a stand-in for primordial gas, show that magnetic fields can dramatically alter how material swirls, transforming chaos into order. If strong enough, they might have whipped early galaxies into shape faster than gravity alone could manage. The stakes go far beyond spinning disks. If ancient galaxies rotated differently, it implies the rules of structure formation weren't just simpler. They were fundamentally altered by conditions we've never witnessed. Each discovery peels back another layer, revealing a universe that didn't just evolve, it improvised, finding paths to order we're only beginning to trace. Globular clusters sparkle like cosmic time capsules, tightly packed spheres of ancient stars that have survived nearly as long as the universe itself. While most cling to the outskirts of modern galaxies like celestial barnacles, their origins remain one of astronomy's deepest puzzles. Could these dense stellar swarms be the stripped-down skeletons of the first galaxies, their outer stars ripped away by eons of collisions, leaving only their tough cores behind? The answer might rewrite our understanding of how cosmic structures took shape. Take Omega Centauri, the Milky Way's largest globular cluster, weighing in at over 4 million stars. Unlike typical clusters where stars share near-identical compositions, Omega Centauri's inhabitants vary wildly in heavy elements, a fingerprint suggesting it wasn't born from a single gas cloud, but might instead be the remnant nucleus of a dwarf galaxy devoured by the Milky Way long ago. Its star's chemical diversity mirrors patterns seen in intact dwarf galaxies, as if we're glimpsing the galactic equivalent of an archaeological dig site where layers of stellar history have been compressed into a single glittering orb. The smoking gun lies in the cluster's oldest stars, which predate most of the Milky Way's disk. Spectroscopic studies reveal some contain almost no elements heavier than helium, a hallmark of stars forged from primordial gas untouched by earlier supernovae. Their iron content is often 1,000 times lower than our Sun's, matching predictions for stars born in the universe's first proto-galaxies. Even more telling, their orbits don't align with the Milky Way's rotation, but instead plunge chaotically through the galactic halo, like survivors of a long-vanished system. Modern telescopes are revealing even stranger clues. The Hubble Space Telescope spotted a population of young blue stars in some clusters, an anomaly for structures thought to have stopped forming stars over 12 billion years ago. One theory suggests these rebels were born from gas squeezed during collisions between clusters, a late-stage burst of creation in otherwise fossilized systems. Meanwhile, the James Webb Space Telescope has detected unexpected amounts of dark matter tugging at certain clusters, a trait far more typical of galaxies than star clusters. Simulations add fuel to the fire. When scientists model the early universe, they find that small proto-galaxies with dense cores could have been shredded by gravitational tides, their outer stars scattered while their central regions held tight, essentially transforming them into what we now call globular clusters. Some virtual universes even produce cluster populations with mass distributions eerily similar to those observed, down to the way their stars clump in distinct chemical subgroups. Yet contradictions linger. A few clusters, like M54, clearly belong to dwarf galaxies like the Sagittarius dwarf, supporting the galactic remnant idea. But others show no signs of ever being part of larger structures, their stars too chemically uniform to have originated in a full-fledged galaxy. This duality suggests globular clusters might have multiple origin stories, some born as galaxies, others as dense star-forming knots in the early cosmic web. The implications ripple across astronomy. If some clusters are fossil galaxies, their stars could preserve unique details about the first stellar generations that larger galaxies blurred through eons of mixing. Their motions might even trace the Milky Way's growth, marking where and when it cannibalized its smaller neighbors. Every flicker of starlight from these ancient spheres carries secrets, not just about how clusters formed, but how the universe learned to build structures from chaos. The cosmic dawn didn't flip on like a switch. It flickered, sputtered, and illuminated the universe in fits and starts. Reionization, the process that transformed the early cosmos from a fog of neutral hydrogen into a transparent expanse, wasn't a uniform wave of light. It was a patchwork of brilliance and shadow, with some regions blazing to life while others lingered in darkness. This uneven glow hints at a universe far more chaotic and unpredictable than our tidy models suggest, where the very first stars and galaxies didn't just light up the cosmos, they rewrote it in erratic strokes. One key to this patchiness lies in the uneven distribution of the universe's earliest stars. population 3 stars, those primordial giants, weren't sprinkled evenly across space like modern stars. Instead, they clustered in dense pockets where dark matter's gravity had pulled together the most gas. Picture a city skyline at night. Some neighborhoods blaze with light while others remain dim. In these bright zones, ultraviolet radiation from massive stars ionized hydrogen in violent bursts, carving out bubbles of transparency. But between them, vast stretches of neutral gas persisted, absorbing starlight like a cosmic sponge. The James Webb Space Telescope has spotted hints of this mosaic pattern in distant quasars, whose light passes through alternating regions of ionized and neutral gas like headlights piercing fog. But stars weren't the only players. The first galaxies, too, contributed to this flickering landscape. Small, early galaxies produced UV photons inefficiently, their radiation often trapped by surrounding gas before it could escape and contribute to reionization. Larger galaxies, though rarer, were photon factories, their intense radiation punching through gas clouds to ionize far wider regions. Simulations show these galactic heavyweights acting like lighthouses, their beams cutting through the cosmic haze in narrow cones rather than omnidirectional glow. The result, a universe reionized in jagged, unpredictable patches, where proximity to a bright galaxy meant early clarity, while isolated regions languished in primordial fog. Then there's the wild card of feedback. As UV radiation ionized gas, it also heated it, making it harder for nearby galaxies to pull in fuel for new stars. In some areas, this stifled further star formation, creating self-limiting bubbles where reionization stalled. Other regions, though, experienced runaway effects. Ionization triggered more star formation, which produced more UV photons, which ionized even more gas. It's like a forest fire that sometimes burns itself out and other times spreads uncontrollably, governed by the whims of wind and terrain. The echoes of this flickering dawn linger in the cosmic microwave background. Tiny fluctuations in its polarization reveal where reionization began earliest and lasted longest, painting a map of the universe's first light. But the story isn't just about photons and gas, it's about how the cosmos learned to sculpt itself, one erratic glow at a time. Every patch of shadow, every burst of light was a stepping stone toward the transparent universe we call home. The violent deaths of the universe's first stars didn't just scatter stardust, they sculpted the cosmic landscape itself. When those primordial behemoths exploded, their shockwaves became cosmic wrecking balls and construction crews, simultaneously tearing apart fledgling gas clouds while seeding the materials for new galactic generations. This feedback loop where destruction fuels creation holds the key to understanding why galaxies look the way they do today. Take supernova winds, the hurricane force outflows from dying population 3 stars. These weren't gentle breezes, they were supersonic tsunamis blasting through surrounding gas at millions of miles per hour. Simulations show how these winds carved vast cavities in the primordial hydrogen, like bubbles rising in boiling water. Within these empty pockets, conditions became perfect for a second wave of star formation, the gas at the bubble edges compressed by the shock fronts into dense, cool sheets ripe for gravitational collapse. It's nature's ultimate recycling program, the ashes of dead stars becoming the nurseries for their successors. But the impact went far beyond simple chemistry. These explosions determined the very structure of early galaxies. In regions where multiple population 3 stars died in quick succession, their combined supernova could eject all remaining gas from a protogalaxy, effectively sterilizing it. We see possible descendants of these stunted galaxies today, ancient, metal-poor dwarfs like Segway 1, which appears to have formed all its stars in a single burst before going dark. Meanwhile, galaxies that managed to retain some gas developed more complex structures, their surviving clouds enriched with heavier elements that allowed for varied stellar populations. The timing of these explosions created cosmic domino effects. early, rapid supernova from massive population, three stars could clear star-forming regions before smaller stars had finished forming, potentially explaining why some ancient star clusters show surprisingly uniform ages. Later generations of stars benefited from this brutal pruning, their formation occurring in environments where feedback mechanisms had already removed the most disruptive turbulence. This delicate dance between creation and destruction may explain why later galaxies like the Milky Way display such organized spiral structures, while their ancestors resembled chaotic, clumpy messes. Some of the most compelling evidence comes from ghostly imprints in modern stellar populations. Stars forming shortly after population, 3 explosions show distinct chemical patterns, unusually high ratios of alpha elements like oxygen and magnesium to iron, matching what models predict from pair instability supernova. Others, like the rare hyper-metal-poor star He-1307-0402, contain barely any iron at all, suggesting they formed from gas touched by just 1 or 2 primordial supernovae before the interstellar medium became well mixed. These celestial fossils preserve snapshots of feedback processes frozen in time. The reach of these first stars extended far beyond their immediate surroundings. Their ultraviolet radiation, streaming through the early cosmos, heated intergalactic hydrogen to temperatures that altered how and where future galaxies could form. This cosmic warming suppressed star formation in low-mass dark matter halos, effectively setting a minimum size for viable galaxies, a possible explanation for why we don't see as many tiny satellite galaxies as theory predicts. The legacy of population 3 stars wasn't just in the materials they created, but in the invisible boundaries they drew across the cosmos. Every galaxy we see today carries their fingerprints, shaped by forces unleashed when the first lights flickered out. The early universe was a chemist's nightmare, an era where hydrogen and helium were the only elements on the periodic table, and every gas cloud was pristine, untouched by the pollution of heavier atoms. Yet today, despite scanning the farthest reaches of space, astronomers can't find a single cloud of gas that remains truly primordial. These cosmic relics should still be drifting between galaxies, frozen in time like bubbles of the universe's infancy. Instead, every measured wisp of interstellar gas bears traces of metals, carbon, oxygen, silicon elements forged in stars that didn't exist when the cosmos began. So where did all the pure hydrogen-helium clouds go? The answer might rewrite our understanding of cosmic recycling. One possibility is that the universe mixed itself far more efficiently than we ever imagined. Supernova didn't just seed the cosmos with heavy elements, they launched shockwaves that churned the interstellar medium like a blender, scattering metals far and wide. Imagine dropping dye into a glass of water. Even if you only stir one corner, eventually the entire glass changes color. Now scale that up to galactic proportions, with shockwaves from dying stars crisscrossing space for billions of years. Even regions untouched by star formation could have been contaminated by these galactic tsunamis, their pristine gas tainted by trace amounts of metals carried across unimaginable distances. Supporting this, computer simulations show that metals disperse rapidly through cosmic filaments, the ribbons of gas connecting galaxies, spreading pollution like ink through a sponge. But mixing alone might not tell the whole story. Another culprit could be the unrelenting glare of starlight itself. Ultraviolet radiation from the first stars didn't just ionize hydrogen, it also broke apart the fragile molecules that help gas cool and clump together. Without these molecular coolants, pure hydrogen-helium clouds would have remained too warm and diffused to shield themselves from further contamination. Over time, these clouds might have dissipated into the cosmic web, their atoms scattered too thinly to ever coalesce into detectable structures. The James Webb Space Telescope has spotted ghostly remnants of this process, ancient gas clouds so tenuous they barely glow, their spectral lines revealing traces of metals that shouldn't be there, like finding footprints in a place no one should have walked. Yet here's the twist: some gas clouds should have escaped. The vast voids between galaxy clusters, regions spanning millions of light years with almost no stars, should, in theory, harbor pockets of primordial gas. These cosmic deserts have remained isolated since the Big Bang, far from the contaminating influence of supernova. But even there, sensitive instruments like the Very Large Telescopes use spectrograph to detect faint metal signatures. One explanation: cosmic rays, high-energy particles accelerated by black holes and exploding stars, might have bombarded these isolated clouds, fusing some hydrogen and helium nuclei into heavier elements right where they float. It's nature's ultimate alchemy, turning nothing but time and energy into atoms that shouldn't exist. The implications are staggering. If no pristine gas survives, it means the universe never preserved a single corner untouched by stellar fires. Every atom we see, even in the deepest voids, carries the echo of some long-dead star's furnace. Yet the hunt isn't over. Astronomers continue scanning the cosmic shadows, hoping to find one surviving relic, one whisper of the universe before chemistry began. Because hidden in that untouched gas might be clues to conditions we can't recreate, a frozen moment waiting to rewrite our story of cosmic dawn. CR7 isn't just another galaxy, it's a cosmic rebel, shining from the early universe with a brilliance that defies explanation. Discovered in 2015, this distant beacon gets its name from its coordinates in the sky, but its real identity remains one of the most heated debates in astrophysics. Its spectrum, the fingerprint of its light, reveals something astonishing: an overwhelming surge of helium emission lines paired with a near-total absence of heavier elements. This bizarre combination has led some scientists to declare CR7 a living relic, a galaxy where the universe's first stars, population 3, might still be burning. Others argue it's hiding something even more extreme. A quasar are so powerful its glare outshines the host galaxy's stars entirely. The case for population 3 stars rests on CR7's eerie purity. The helium emission suggests intense ultraviolet radiation, exactly what you'd expect from massive, metal-free stars. Unlike modern stars, which are polluted with heavier elements, population 3 stars would have burned hot and fast, their UV light ionizing surrounding helium gas and causing it to glow like a neon sign. CR7's spectrum matches these predictions almost perfectly, with no trace of the carbon or oxygen lines typically seen in later galaxies. It's as if we've stumbled onto a cosmic time capsule, a pocket of the universe that somehow avoided contamination for over 13 billion years. Then there's the luminosity problem. CR7 isn't just unusual, it's blinding, shining with the brightness of hundreds of billions of suns. This is where the quasar theory gains traction. Supermassive black holes feeding at the hearts of galaxies can outshine every star in their host combined. If CR7 harbors one of these monsters, its light could mimic the helium signature we associate with population 3 stars. Gas swirling into a black hole's accretion disk heats to millions of degrees, producing UV radiation capable of ionizing helium just as effectively as primordial stars. Some astronomers point to flickering in CR7 brightness, a hallmark of quasars, whose turbulent disks often vary in output over time. But here's where the mystery deepens. High-resolution observations from the James Webb Space Telescope reveal CR7 isn't a single point of light, but a collection of 3 distinct clumps. One glows fiercely with that telltale helium signature, while the others show more typical stellar populations. This structure complicates both theories. If the bright clump were a quasar, why isn't it centered in the galaxy? And if it's a cluster of population 3 stars, how did it form alongside more conventional stars in the same system? The answer might lie in the chaos of the early universe. Simulations suggest that CR7 could be a snapshot of a proto-galaxy caught mid-collision, where shock waves from merging gas clouds triggered simultaneous bursts of different star types. The helium-rich clump might be a nest of population 3 stars born from pristine gas, while the others formed from slightly polluted material nearby. Alternatively, the entire system could be illuminated by a wandering black hole, a relic of an earlier galaxy collision, now rampaging through CR7 gas clouds and igniting them like a match tossed into dry leaves. The implications stretch beyond one galaxy. If CR7 truly hosts population 3 stars, it proves that pockets of the primordial universe survived longer than we thought, offering a rare chance to study these cosmic pioneers directly. If it's a quasar masquerading as something older, it challenges our assumptions about how quickly black holes grew and how they shaped their surroundings. Every new observation peels back another layer, revealing a universe where the rules weren't just different, they were being rewritten in real time. CR7 isn't just a mystery, it's a mirror, reflecting our own struggle to decipher a past more complex than we ever imagined. The dark matter blanketing our universe isn't just mysterious, it might have rewritten cosmic history depending on how cold or warm it behaved in the early cosmos. This isn't about temperature in the everyday sense, it's about speed. Cold dark matter moves sluggishly, its particles lumbering like giants through the primordial universe, while warm dark matter zips along at near light speeds, its lightness making it more restless. That distinction might sound subtle, but it's the difference between a universe where galaxies form in an orderly hierarchy and one where they burst onto the scene in a chaotic frenzy. Simulations of cold dark matter paint a familiar picture, tiny clumps of matter slowly merging into larger structures like droplets of water combining to form puddles, then lakes, then oceans. This bottom-up growth neatly explains the cosmic web we see today, vast filaments of galaxies strung together by dark matter's invisible scaffolding. But when astronomers peer back to the universe's first billion years, the model stumbles. Where are the countless dwarf galaxies these simulations predict should orbit larger ones like the Milky Way? Why do some ancient galaxies appear too massive too soon? The cold dark matter paradigm starts to crack under these early universe extremes. Enter warm dark matter. If dark matter particles were even slightly lighter and faster, they'd resist clumping on small scales, smoothing out the universe's initial wrinkles. This would suppress the formation of tiny dwarf galaxies while allowing massive ones to emerge earlier, closer to what telescopes like James Webb actually observe. Picture the difference between building a sandcastle with wet, clingy sand versus dry, fine grains. Cold dark matter acts like the wet sand, sticking easily into small clumps, while warm dark matter resembles the dry grains, requiring larger structures to hold together. Some modified theories even propose a middle path, fuzzy dark matter, where particles are so light they behave like quantum waves, creating a universe with fewer, fluffier, small-scale structures. Yet warm dark matter has its own contradictions. If it prevented small galaxies from forming, why do we still see some ultra-faint dwarfs in our cosmic backyard, like Segway 1 or Draco? Their existence suggests that whatever dark matter is, it must allow for at least some minuscule structures. Then there's the Lyman-Alpha forest, the intricate pattern of absorption lines in quasar light caused by intervening gas clouds. These patterns closely match cold dark matter predictions, with a spectrum of clumpiness that warm dark matter struggles to replicate perfectly. The most tantalizing clues might come from the cosmic microwave background's faintest fluctuations. Planck satellite data slightly favors cold dark matter, but anomalies linger at small angular scales, hints that dark matter's true nature could be more complex than either extreme. Certain alternative models, like self-interacting dark matter, propose particles that collide like molecules in a gas, smoothing out small-scale structures without requiring unreasonable speeds. Others explore sterile neutrinos, hypothetical particles just heavy enough to act cold, but with a kick of warmth that alters galaxy formation's early stages. What's at stake isn't just a tweak to astrophysical models. If dark matter is warmer than we thought, it could mean the particles themselves are fundamentally different, perhaps connected to neutrinos or other elusive quantum fields. Alternately, if cold dark matter holds firm, we might need entirely new physics to explain why the early universe looks so unexpectedly mature. Every simulation, every observation, pulls us deeper into the mystery, revealing a cosmos where the invisible majority doesn't just watch from the shadows, it dictates how the visible universe learns to shine. The first stars didn't just burn differently, they lived at a pace that would make modern stars seem like lazy giants. Population 3 stars, those cosmic pioneers forged from pure hydrogen and helium, raced through their lives with a ferocity unmatched in today's universe. While a star like our Sun will shine steadily for billions of years, these primordial behemoths likely blazed for mere millions, some perhaps as briefly as 2 million years, a cosmic blink before vanishing in spectacular fashion. But their brevity wasn't random. It was written in their mass, a brutal equation where size dictated destiny. The most massive population, 3 stars, those tipping the scales at over 100 times the Sun's weight, were cosmic shooting stars. Their immense gravity crushed their cores to unimaginable pressures, igniting nuclear fusion at rates that devoured their fuel like a wildfire in dry grass. Models suggest these titans burned out in under 3 million years, their cores growing so hot they triggered runaway reactions that obliterated them completely in pair instability supernova. No black holes, no neutron stars, just a titanic explosion scattering newly forged elements into the void. Stars slightly smaller, between 60 and 100 solar masses, might have lasted 5 to 10 million years before meeting similar fates, their deaths no less violent but slightly more predictable. But what about the smaller population 3 stars? If any existed below 60 solar masses, a point still debated they could have lived longer, perhaps 30 to 50 million years. Still a fleeting existence by stellar standards, but long enough to influence their surroundings in subtler ways. Instead of vanishing in apocalyptic blasts, these stars might have collapsed directly into black holes, their outer layers imploding silently, locking away their heavy elements forever. This split in fates created a cosmic divide. The universe's first chemical enrichment came not from a steady drizzle, but from intermittent catastrophic downpours. The implications ripple through time. Stars that died as pair instability supernova didn't just explode, they cooked up elements in ways later stars never could. Their extreme temperatures fused hydrogen and helium into carbon, oxygen, and even silicon in a single, furious burst, elements that would later form the backbone of planets and life. Yet these explosions were picky alchemists. Unlike modern supernova that produce a broad palette of heavy elements, pair instability events favored even-numbered elements like oxygen and magnesium, leaving oddities like lithium or boron curiously scarce. Traces of this bias linger in the Milky Way's oldest stars, their atmospheres bearing chemical fingerprints of these selective cosmic forges. Meanwhile, stars that collapsed into black holes left a different legacy. By locking away their heavy elements, they created cosmic dead zones, regions where the next generation of stars formed from nearly pristine gas, resetting the chemical clock. This might explain why some ancient stars, like the enigmatic SMSS 0313-6708, show bizarre element ratios untouched by later supernova. Their birth clouds could have been shadowed by silent black holes, ghostly remnants of stars that chose disappearance over fireworks. The lifespan of these first stars wasn't just a matter of stellar physics, it shaped the universe's capacity for complexity. Longer-lived stars might have allowed for gentler, more continuous enrichment, building up heavy elements gradually. Instead, their short, violent lives made cosmic chemistry a stop-start process, with periods of frantic creation followed by eerie quiet. It's a rhythm still echoed in the galaxies we see today, clusters of metal-rich stars interspersed with ancient metal-poor holdouts, all dancing to a tune set by the first star's fleeting brilliance. Imagine stars that don't shine through nuclear fusion but burn with the eerie glow of annihilating dark matter. This is the radical premise behind dark stars, hypothetical celestial giants that might have littered the early cosmos, fueled not by ordinary fire, but by the mysterious collisions of invisible particles. While conventional stars fuse hydrogen in their cores, these shadowy counterparts could have drawn energy from dark matter particles colliding and destroying each other, releasing heat that prevented gravitational collapse from triggering normal fusion. The result, stars that would grow to staggering sizes, potentially millions of times more massive than our Sun, and radiate a cold, steady light unlike anything in the modern universe. The theory hinges on dark matter's elusive properties. If certain types of weakly interacting massive particles WIMP existed in dense clumps within early galaxies, their mutual annihilation would release torrents of energy. In regions where dark matter outweighed ordinary matter, this process could have sustained protostars indefinitely, creating objects that balloon to absurd proportions while maintaining relatively cool surface temperatures. Picture a cosmic hot air balloon expanding as heat pours in, never quite reaching the critical density needed for hydrogen fusion to ignite. These dark stars would have glowed with a diffuse, reddish light, their surfaces barely hotter than a campfire despite their unimaginable bulk. The James Webb Space Telescope might hold the key to confirming their existence. Astronomers are scouring its deep field images for unusual infrared signatures, objects too large and too dim to be conventional stars, yet too bright to be failed protostars. One tantalizing candidate, JWST 13-0, shows spectral features that don't quite match predictions for early galaxies or population Roman III stars. Its light profile hints at something vast and oddly distributed, like a faint smudge where a pinpoint of starlight should be. Could this be the ghostly afterglow of a dark star, its light stretched and reddened by billions of years of cosmic expansion? Critics raise valid concerns. If dark stars existed, why haven't we spotted their remnants? Some models suggest these objects would eventually accumulate enough normal matter to trigger fusion, transforming into supermassive stars that collapse into black holes, the possible seeds of today's quasars. Others argue that dark matter annihilation would have been too inefficient to sustain such structures, leaving them as fleeting anomalies in a universe dominated by fusion-powered stars. Yet the possibility remains enticing because it solves multiple puzzles at once. The unexpected maturity of some early galaxies, the rapid growth of supermassive black holes, and even the distribution of dark matter halos we observe today. What makes the hunt so revolutionary isn't just the chance to find a new class of stellar objects, it's the opportunity to probe dark matter's nature directly. If dark stars left detectable imprints, their spectra could reveal the mass and interaction cross-sections of the particles that powered them, offering clues to a mystery that's defied physicists for decades. Every anomalous infrared glow, every odd luminosity pattern in Webb's data could be a breadcrumb leading us toward understanding the invisible scaffolding of reality itself. The universe's first light might not have been what we thought, and the darkest corners of physics could hold the key. The universe isn't just a scatter of stars and galaxies, it's a vast, intricate spiderweb with strands of dark matter and gas stretching billions of light years to connect everything in a delicate cosmic lattice. This grand architecture, known as the cosmic web, didn't form by accident. Its blueprint was etched by the very first stars, whose explosive lives funneled gas into the filaments we see today, shaping the distribution of galaxies for all time. But how did these solo acts of stellar brilliance become the architects of the largest structures in existence? The answer lies in the interplay of fire and gravity, where the deaths of stars forged the highways along which the universe would forever build. Picture the aftermath of a population 3 supernova, a blast so powerful it could outshine an entire galaxy. As these titans exploded, they didn't just spew heavy elements into the void, Their shockwaves plowed through surrounding gas, shoving it outward like a snowplow clearing a path. These expanding bubbles of hot, metal-rich material collided with neighboring structures, sweeping up neutral hydrogen and compressing it into dense sheets and tendrils. Simulations reveal how these collisions created a patchwork of high-pressure ridges, cosmic fault lines where gravity later drew gas into the filaments of the cosmic web. It's as if each exploding star planted seeds of structure, its death throws tilling the soil for future galaxies to grow. Yet the story isn't just about brute force. The first stars also shaped the web through their light. Ultraviolet radiation from these early beacons ionized the surrounding hydrogen, heating it until it became too energetic to collapse into small clumps. This created a cosmic sorting system. Ionized gas pooled into vast, diffuse reservoirs along dark matter's invisible scaffolding, while cooler, neutral hydrogen slid into the densest intersections, fueling the birth of galaxies. The result was a universe partitioned into bright nodes linked by luminous threads, a skeleton where gas flowed like blood through veins, feeding growth where gravity demanded it most. The fingerprints of this process linger in modern galaxy surveys. Megaprojects like the Sloan Digital Sky Survey show galaxies strung along filaments like pearls on a necklace, their positions tracing paths laid down over 13 billion years ago. Even more telling, the gas between galaxies, the intergalactic medium, bears the chemical signature of those first stars. Heavy elements like carbon and oxygen, forged in primordial supernova, are sprinkled even in the web's emptiest regions, proof that early stellar winds blasted material far beyond their birthplaces. But the cosmic web isn't static. Like a living network, it pulses with gas flowing from voids into filaments, then funneling toward galaxy clusters in a slow-motion deluge. The James Webb Space Telescope has caught glimpses of this in action, streams of gas glowing faintly as they spiral into ancient galaxies, their motions echoing the gravitational hum of dark matter's unseen hand. Some of these flows may be direct descendants of channels carved by the first stars, their paths set in motion when the universe was young and malleable. What's staggering is the scale of this legacy. A single generation of stars burning bright and dying young didn't just light up the cosmos, they gave it shape. Their explosions dictated where galaxies would bloom, their radiation cleared the fog that obscured the web's design, and their chemistry enriched the rivers of gas that still feed star formation today. The universe didn't weave itself by chance, it was sewn together by the sparks and ashes of its first firemakers. Not all corners of the early universe woke up at the same time. While some regions blazed to life with the first stars and galaxies, others lingered in darkness like cosmic late sleepers, and the difference came down to a perfect storm of conditions we now call the Goldilocks zone for galaxy formation. Picture the primordial cosmos as a lumpy batter, with denser regions where gravity got an early head start, pulling together gas and dark matter into the first protogalaxies. But density alone didn't decide which regions would ignite first. The local environment played cosmic referee, with factors like radiation, turbulence, and even the aftermath of nearby explosions tilting the scales toward star formation or slamming the brakes on it. Take the cosmic variance in density fluctuations left over from the Big Bang. Quantum ripples in the universe's infancy stretched to macroscopic scales during inflation, creating slightly overdense patches where dark matter began pooling earlier. These became the kernels of future galaxies, but their growth wasn't guaranteed. Ultraviolet radiation from the first stars, once they formed, could flood neighboring regions, heating gas and stifling collapse elsewhere. It's like a forest fire where the first flames create wind patterns that either spread or starve nearby sparks. Simulations show these feedback loops created a patchwork of feasting and famine. Some protogalaxies gorged on cool, dense gas, while others were left gasping in the radiative heat. Then there's the wild card of cosmic filaments, the universe's hidden transportation network. gas streaming along these dark matter highways didn't flow evenly. Knots where filaments intersected became gravitational hubs, funneling material into dense nodes ripe for star formation. Off the beaten path, gas remained diffused, delaying galaxy birth for hundreds of millions of years. The ALMA telescope has spotted this in action, revealing ancient galaxies clustered along invisible threads like jewels strung on a necklace, their positions dictated by the cosmic web's underlying skeleton. But the true tipping point might have been chemical. Regions enriched by early supernovae saw their gas cool faster, thanks to heavy elements that radiated heat away more efficiently. This created a snowball effect. Faster cooling meant quicker star formation, which led to more supernova and even faster cooling. Meanwhile, pristine regions struggled to condense, their gas too warm to collapse without those crucial metals. It's the difference between trying to freeze a glass of purified water versus a slushy saltwater mix. One resists solidifying, while the other crystallizes almost instantly. The legacy of these Goldilocks zones is written in the heavens. Today's galaxy clusters trace the outlines of those early overdensities, their brightest members descendants of the regions that hit the cosmic jackpot, are just dense enough, just cool enough, and just lucky enough to catch the universe's first wave of starlight. Every galaxy we see, from spirals to dwarfs, carries the imprint of a time when the universe played favorites, and the rules of engagement were still being forged. The first galaxies weren't built to last. Born in the chaos of the early universe, these fragile collections of stars faced a brutal fate, crushed by collisions, cannibalized by growing giants, or fading into obscurity as their star-forming gas was stripped away. Yet against all odds, traces of these pioneering structures might still linger in our cosmic neighborhood, hiding in plain sight as galactic fossils. Finding them would be like stumbling upon a medieval castle buried beneath a modern city, a relic of a forgotten age, reshaped but still recognizable. One possibility is that some primordial galaxies avoided destruction by sheer isolation. In the sparse voids between galaxy clusters, a few early dwarfs might have drifted untouched for billions of years, their gas too diffused to fuel mergers and their stars too few to attract attention. Ultra-faint dwarfs like Segway 1, orbiting the Milky Way with just a few hundred ancient stars, could be the last survivors of this kind, galaxies so small and dim they slip through the cracks of cosmic evolution. Their stars show near pristine chemistry, with metal contents 1,000 times lower than our sun's, as if frozen in time since the universe's first chapters. But mergers tell a different story. Most primordial galaxies were dismantled and absorbed by growing giants like the Milky Way, their stars scattered into the galactic halo like ingredients stirred into a soup. Astronomers reconstruct these ancient collisions by tracking stellar streams, rivers of stars winding through our galaxy's outskirts, each marking the grave of a devoured dwarf. The Gaia Space Telescope has mapped dozens of these ghostly remnants, including the massive Gaia-Enceladus merger, whose stars account for nearly half the Milky Way's halo. These aren't just cosmic archaeology, they're proof that the first galaxies live on, not as intact structures, but as the foundation stones of everything we see today. Then there's the radical idea that some primordial galaxies transformed rather than vanished. In dense environments, tidal forces and ram pressure might have stripped away a dwarf galaxy's gas while leaving its core intact, creating relic galaxies that stopped forming stars early. Objects like NGC 1277 in the Perseus cluster fit this description: compact, red, and eerily quiet. They resemble black and white photos of the universe's youth. If any population 3 stars still burn within them, they'd be cosmic time capsules preserving the conditions of the first starlight. The James Webb Space Telescope is now hunting for these living fossils in unprecedented detail. Its infrared eyes can peer through dust to spot galaxies so ancient they appear frozen in time, their light stretched by cosmic expansion into deep red hues. One candidate, the sparkler galaxy, glitters with dense star clusters that may be the cores of primordial dwarfs swallowed long ago. Others, like the unusually pristine galaxy JWST 701QU, show chemistry so primitive they could be direct descendants of the first star-forming systems. Yet the most tantalizing clues might come from our own backyard. The Milky Way's satellite galaxies, once dismissed as ordinary dwarfs, are now revealing secrets. Some, like Draco and Ursa Minor, rotate in a single plane, a configuration that suggests they're remnants of a larger structure torn apart eons ago. Others, like Triangulum 2, contain stars with bizarrely low metal content, their composition matching simulations of galaxies that formed before reionization. If confirmed, these could be the closest living relics of the cosmic dawn, orbiting our galaxy like ghosts at the feast. The ultimate fate of the first galaxies isn't just a question of history, it's a mirror. By studying how they evolved, we're glimpsing the future of our own Milky Way, destined to collide with Andromeda in 4 billion years. Their stories remind us that the cosmos doesn't erase its past, it weaves it into the present, one merger, one transformation, one hidden survivor at a time. Every faint star, every silent dwarf, every twisted stream is a testament to where we came from and where we're going. From the blazing birth of population, 3 stars, to the ghostly traces of dark matter shaping the cosmos, these 30 mysteries aren't just riddles, they're the scaffolding of our cosmic origin story. Each one peels back another layer of the universe's first moments, revealing how the simplest ingredients, hydrogen, helium, and gravity, cooked up everything we see today. The enigma of primordial black holes rewrites how structure emerged. The missing dwarf galaxies challenge our grasp of dark matter. The flickering of reionization shows a universe learning to shine. Even the violent deaths of the first stars weren't endings, they were the alchemy that forged the elements in your bones, the screen you're watching, the air you breathe. But the most thrilling part, half these mysteries might be solved within our lifetime. Telescopes like the James Webb Space Telescope and the upcoming Nancy Grace Roman Observatory are already rewriting textbooks, while gravitational wave detectors listen for echoes of ancient black hole collisions. The European Extremely Large Telescope, with its 39-meter mirror, could capture starlight from the universe's first billion years in unprecedented detail. And projects like the Square Kilometre Array will map the cosmic dawn's radio whispers, turning static into a story. Yet for every answer, new questions erupt. Are dark stars still glowing somewhere in the void? Did some population 3 stars survive, hidden in galactic backwaters? What strange physics governed the universe before the first light? The beauty isn't in solving these puzzles, it's in realizing how much we've yet to discover. The cosmos didn't just unfold in the past, it's unfolding now in real time, with every observation, every dataset, every curious mind peering into the dark. So stay hungry, follow the trails of those first starlit pioneers, because their secrets are still out there, written in quasar light, encoded in ancient gas, waiting in the next snapshot from a telescope not yet built. The universe's greatest story isn't finished, and the next chapter, it's yours to explore.